I will finally finish that paper on circuits and arithmetic. And then we are going to do a little review of the first part of the course, since we are now in the last lecture before the spring break. And to do that, we are going to, I don't know how much time we are going to have, but basically I can show you how I structured it. So for every method we have kind of covered, we are going to go over pros and cons, and you guys are going to tell me, oh, what is this method or this assumption good for, what are its limitations, and then we are going to discuss a little bit like what to do then in practice. And you'll see, there are many of these. It turns out we actually covered a lot. So we'll see how much we cover, but that's basically what we are going to do today. Before I go into that paper, I do want to remind you of a bunch of announcements that Fatima and I sent yesterday. So every one of you now should have comments on your Google Doc for your proposal. And depending on proposal to proposal, you might have received a request for revisions or not, a meeting or not, and so on. If you have a meeting with me tomorrow, keep in mind that now I have a stack of 15 minutes meetings, one after the other. So you need to be ready to use those 15 minutes well. Just FYI, you can always, when you schedule meetings with me, take more than one meeting, and then you have, like, if you need 30 minutes, you will, take two, one after the other. So what I suggest is that to prepare just one slide where basically what we need to discuss is your revision plan, right? Like what is that you're going to do, and I just want to give you my feedback of whether that sounds good so you can continue working on your projects. I just want to make sure you are in a good spot tomorrow. So what I recommend is have a slide and tell, all right, in general, one sentence, this is what we are trying to achieve, and these are the experiments we are planning for our goal. And I think that can take like 5 minutes, and then we can have 10 minutes for discussion. I definitely wasn't clear on what I expect from the proposal, so I received a varying level of formality, and that's on me, and this is why I said I will, if you integrate my regions, everyone will get the points. But just moving forward, keep in mind that I'm looking for a more formal language, and that doesn't mean, oh, I need to use complicated words and long sentences. If anything, it's the opposite. I want to have formal but clear, concise language, right? So this is also your practice to kind of write more like scientific writing, right? And when you're writing the proposals, to have that level of formality. Many of you are working with tracing sparse feature circuits, and Fatima's code is going to come handy for that. So she shared here her repository for doing that, and then I didn't quite read your announcement, Fatima, sorry, but I suppose if students have questions, they can reach out to you. Yeah. And then another thing I have noticed is that by the time I sent this announcement, one student had made a CHPC account. Many more have made since then, so thank you for reacting to this message. Basically now I do request you to run something on CHPC, and Fatima shared an announcement about that. We would like you to do this, if possible, by end of this Friday, just to give you some sense of urgency. If you have some other deadlines and this is impossible, just let us know. But the reason why we want to force you to run something on CHPC, we really want to avoid the situation where you need to run your jobs on CHPC, and that's the first time you're learning how to do that, right? When you want to run your experiment, you already want to have a mental model of how CHPC works and what should you do to actually, run a job on a GPU, on CHPC. So yeah, do that. It should be pretty straightforward. You just Fatima may have given you instructions, but you have a code that you're going to run. So you don't write any code. It's just about successfully scheduling the Solana job with it. Okay, and then for what to expect next on March 23rd, which is a Monday, you're going to submit your intermediate report. And that intermediate report is basically, you already have questions after your project proposal. So these are the questions going to pair two teams, and you are going to read the proposal and report of the other team. And then on Thursday of that week, when you come here, you are going to discuss with the other team, okay, we didn't quite understand this. Like, you will try to, through conversation, clarify anything that's unclear, give suggestions of what you would maybe try and things like that. In this way, if other team tells you, I really didn't understand why you're doing this, this gives you a signal, well, motivation for this experiment isn't quite clear, and I should, by the time I present this for a poster, I should really, clarify for myself what is that I'm doing here, right? So you should think about it in that way. But after the class on Thursday, that Thursday, you are going to then submit this report, and then we are going to report the changes of the report ourselves, not the other students. And I think that's it from the announcements here. Are there any questions about any of this? This was quite a lot, so yeah, I would expect questions. Yeah.
Just to confirm, once we, like, if we adapt your changes into the proposal, we just leave it in the doc, we don't resubmit.
Yeah, that's right, for the proposal part. Yeah, just leave it in the Google Doc because, yeah, I don't need them basically in grade school, is the long story short. Yeah. Okay, so with all of that, let's get going with this part. Okay, so remember that we are going over this paper, and we are going over this paper because it's a great kind of use case of a bunch of things we have learned in the first part of this course. So it's a super nice way to kind of see whether you understand things we have been talking about so far. Basically, while you read the paper, you should have a sense of like, I know what's going on here, I'm kind of following why they use this method and how it was applied. So we are just going to go over it as a kind of a joint practice, and then we are going to go into the reading part. So we have covered this slide about 3 times already. I did have a mistake, and last time I said this is denoising rather than what we're doing nosing, so they made a clean run and they patched it with the corrupt representation. And then I told you that instead of using just the difference of the logic of the correct answer, they are using this a little bit more complicated formula. And in this little bit more complicated formula, they have notion of the clean prompt with the result R. So just a normal equation and the correct result. We have P prime, that's some kind of other arithmetic equation, and result R prime. And then we have probability before patching and probability P star after patching. And basically what this says is both of these summands are going to increase if patching raises the probability of R prime. So you are noising, right? Because the probability of wrong answer is being increased, or it decreases the probability of the just R, which is our clean response, which again is a signal of noising. You want to kind of both of these things to be happening. And again, my kind of takeaway for you here is that you remember that which function you choose for measuring change in behavior from patching is up to you. Now you have learned 2 variants, but if you feel like you have a third idea, which is particularly useful for your case, use it, right? There is no demand that you need to use something specific here. And then we come to something that can be quite confusing given that we have learned these sparse feature circuits. And that's the idea that patching is now giving us a circuit. And this is because if you're feeling a little bit confused of how did we now get the circuit, thinking about sparse feature circuits, you should keep in mind that they're using a whole different notion of what the circuit is. So for them, the circuit is just a collection, a set, instead of like a specific graph, of model components that are important for specific tasks. So activation patching did give them such, attention heads and MLPs, and those that are deemed important by them, they take it as a set, and that's a circuit for them, okay? And then they need to do all these additional steps to actually understand what that circuit is doing. And by doing this additional step, they will find out that for solving arithmetic tasks, this model is going to use that bag of heuristics, right? Okay, so it's really important from this first part of the course that you embrace that there are sparse feature circuits, and then there are just circuits where you don't care about what is a node, right? So when we say feature circuits, we are emphasizing word feature because node has to be feature, right? Like in a Texas, Dallas, Austin example, feature was Texas, an actual, human understandable word. Here, your feature is an MLP head, right? So it's an MLP or attention head. It's much more coarse and less detailed. Now, given that collection of important components, which they call circuit, they check whether that circuit is faithful to the underlying model M. And to do that, they use this equation where we have this function ML, which refers to the logic of the correct answer that's normalized, and it's normalized by the maximum logic in the entirety vector of logits. So if we have a correct answer, right, the correct answer was predicted. Correct answer, because it was predicted, it has the max logic because we use the token that has the max logic to, make a prediction. So whenever the answer is predicted and it's a correct answer, this ML value will be 1. Okay, so now we can take this function with the circuit C, with the full model N, or here we use empty set, but what we actually mean is mean ablating, and we are going to cover all of these cases. So first one is where we take only these important components, and only using them, we are calculating what is the logic, the normalized logic of the correct answer. So, for example, here, let's say we have chosen all the MLPs that have a value that's 6 or higher, so maybe this one's at the top. And instead of passing the input token embedding through every single one of them, we are going to go from here to here to here and so on. So input to a component is the output of the previous important component, right? We are skipping everything else. No, that was actually wrong what I just said. This is, I'm so sorry. I forget in this paper actually, they are not going to skip those. They are going to just everything that's not important. So here, all these, light value, like components corresponding to light values. So they are going to set the representations of those components to the mean value. And mean value is calculated using the entire data set. So let me just specify this a little bit better. If I say, let's say here, my first MLP, not important, I will pass my entire data set to this model and collect all the representation coming out of that MLP. And I'm going to average them, and I'm going to say this is mean version of that representation, and I'm going to override whatever that module would actually say the representation of a given token in a given prompt would be with that mean ablated version. Okay? So I'm sorry, there are people do this in different ways, so I for a moment forget that here they're not like skipping everything, rather they're passing the representation to every layer, but if the component wasn't important based on activation patching, they're going to use mean version of the representation rather than the actual one. Okay, then we have our ML for the full model. That's just a normal logic we get with the normal model, and here we get what a model would say if all of the representations are replaced with the mean version. And the idea here is that this probability, basically, this is not prompt specific, right? We are using some average version of the data set, and this probability actually won't be zero. So you're checking how much this difference between the logic when you get using circuit only is different from what we would get from mean ablating error, right? Because maybe even this will give us somehow high probability, and we do the same thing in the denominator. Okay, and that's it, right? So if this value is close to 1, meaning the logic for the correct answer is similar when we use a circuit or the full model, that means that it suggests that this circuit is a good replacement for the original model for this given prompt, right? And when then we average this across many prompts and the value stays close to 1, then we are saying, okay, my circuit is behaving roughly as the full model. And that's basically what they found. Okay, I deleted it now. Oh, I didn't. At the top I say, in this work, the circuit accounts for 96% of the entire model's performance. So the average faithfulness value here is very, very close to 1. And that's a good signal that components they have found are a good replacement for the original model. Okay, so after they have done that, they also additionally do linear probing. And they first freeze the model that they're using llama 3 abelian, and they train linear classifiers on the components output. So if we zoom in here and we take MLP in layer 20, position 4, we will take the output of that MLP, and we are going to train a linear model over those representations. For the data, we are going to use prompts and correct answers. And if the idea here is, if this linear probe that's linear can predict the correct answer from this representation alone, that, as always with probing, suggests that information was already encoded in the representation itself, because we assume that a simple linear model would not have the capacity to solve these arithmetic tasks unless this information was present. They're just too weak to do this on their own, so there must be information in the representation that gives them that power, right? That's just a premise of linear probing in general. And what I find is that in these layers that are really high here, really very intense, so at the last position where the symbol for equal is, and these mid to late layers, the linear probe is capable of predicting the correct answer, which suggests that these layers are those that encode the correct answer. Okay, so now they have these components and they have information of them being important, but they don't really have information about what these components are doing. And in next sequences of experiments, they are going to try to make sense of what these components are doing to say what the model overall is doing. So next thing they do is yet another activation patching, but instead of taking a full module, MLP or attention head, as a thing we are patching, they take these modules that they found important from the previous two experiments, and they look at their individual neurons, right? And then they do activation patching per neuron in these representations. Quick question, just to see whether you remember what we were talking about last time. What is the challenge here? Why would they want to take only the important modules rather than all modules and check neuron in every single module? There.
To be really slow.
Really slow. Yeah, really slow and really expensive, right? So maybe you don't even have resources to do all of this, right? Or, but yeah, right, it kind of comes down to slowness, because at least you have a CPU, so that will take a very, very long time. So you kind of, this pre-filtering of components is really important here because, just doing activation patching on a level of neurons for all the neurons would be too much. So they do the same thing we have done with the full component with neurons, and one thing they found is that we have a different operator, plus, minus, divide, multiply, and for different operator, they find different neurons activate. So we have neurons specializing for the operand. So they were doing analysis per operand, right? So here, I think that we were looking only maybe at addition, or I'm not sure. But here you can see how they have 4 lines for every one of the operators, right? From this plot, what you can see is the what is the patching effect of patching a neuron. This is a neuron's index, and what you can see is that some of them have much higher values, right? And those are the ones that we deem to be more important, right? Also, here you can see what the same metric of faithfulness that we were using before. Again, now you can define circuit out of neurons, right? And you can use the same equation as we did before. At the y-axis here, you are seeing the faithfulness value. Higher means closer to what the model is doing and what is desirable. And here is the fraction of neurons we are using per lane. What you can see is that here, except with multiplication, when we hit 1% of neurons, we are already recovering most of the model's behavior. So for all of the operands, except for the multiplication, we see that we need roughly 1.5% of the neurons to be able to recover the model's behavior. And that's a really little amount, right? So what they do next is that they are like, the conclusion so far is we have neurons that are specializing for doing this arithmetic, when one can actually answer these prompts. That's okay, but we still don't have a level of like, what are these neurons doing and what is the model doing, right? Like when we say, well, there are 1.5% of the neurons that can do division. That's a nice finding, but that will tell you exactly what the model is doing, right? And now you need to do extra steps to understand the behavior of those neurons. So the first thing they do here, you see what is the output of MLP has. So usually we have the MLP combined with the linear layers. So this is just equation of feed-forward or multilinear perceptron in a transformer block. And they just rearrange it a little bit like this and write it in this way because, and I don't want to go too much into detail of this, but you can see this as like a query value, vectors, and then vectors are those that are writing onto the stream, and those before them are having different behavior. Not entirely important here. What I want you to remember is how are they describing this neuron, and this is basically what we have learned in this course before. So they are going to collect top activating prompts for every single neuron individually. They are going to record the activation across this grid. So you have first operand and second operand. So operand is if you have addition, the first operand and the second operand that are embedded together. So they are restricting operands to be from 0 to 999, and then this value means that if I have addition and I have not necessarily addition, think any operation, and I have all this high value when I have 100 and 100 as operands, right? So you can visualize when the neuron is activated using these heat maps. One day I will trip and it's going to be really fun for you and really not fun for me. We visualize these activation heat maps And then you can they themselves manually observe what's going on in these activations. And actually welcome you to go and check the, I know when I say do something without forcing you, usually you don't have time for it, but I would really welcome you to read this paper. As I said, it's a good way to kind of see whether you understand all these methods. But what I want you to point you to is in the appendix. We have all these nice visualizations of the kinds of, they get the heat map. So this is for the neuron in layer 17, 1,463 neuron. You have for this heat map. So this means this is when this neuron is active or not. Or here you can see a little bit nicer patterns. So these researchers were looking into these patterns, and from them they have, decided what the kind of heuristic they're seeing here. So, for example, here they say the operand 1 is a range of 0 to 50 or 0 to 100, and operand 2 is between 0 and 100. Yes?
This is always two numbers.
Sorry?
The setup here is two numbers not greater than 999.
So two operands, and neither of them is higher than 999. Yeah, so all the operands are of the kind operand 1, so plus, minus, multiply, or divide, operand 2, and equal. That's what I have.
And if we were to extend that to 3 numbers or 10 numbers, would we expect that 200 neurons isn't sufficient and it would have to get bigger?
Oh, yeah. Let's not open that question just yet. But there is a question of how to measure the generalization of these kinds of circuits, and there is a nice work. If you are really, really interested, let me just quickly go find it. Stability. Okay, nice. This one that kind of defines what if our operands have larger and larger digits. So it's not about more and more operands, rather the operands themselves have larger digits. And if I find a circuit for numbers that are a certain range, whether that circuit will, be stable and be, something we observe for adding larger numbers, and they find not really, they don't see this generalization property. The key contribution here is to defining that stability. So what you can see here is basically how performance of JEMMA decreases as the number of digits is becoming higher and higher, and then they connect that with circuits. I hope we get to the point where we can discuss these kinds of works, but if you are interested, I recommend reading this one. Keep in mind that this won't transfer to sparse feature circuits because they have a notion of stability that requires exact component use, and they are not assuming that the node is a feature or a component. Okay, but just going back to this work, I welcome you to kind of check these patterns to get a sense of these heuristics that these models are kind of activating for. So in this way, with this analysis up to here, they get these heat maps and they themselves manually assign a pattern to it. And then the final step is to check for this specific neuron that, let's say they zoom into this neuron, they have produced this heuristic manually, and now they also want to see, well, if I have operands and operation that fires up, or in this way, how does it affect the logics? And this is where they use logic threads, where they take that neuron, they take the unembedded matrix, and they manage to see which of the tokens will activate, be promoted or depromoted by this neuron. And we see here that, okay, if the difference between these two operands is in the range of between 150 and 180, then it promotes 158 as the answer. Okay, so now we have described neuron behavior. We have said what kind of operands this neuron fires up. What is the heuristic that can be used to describe that behavior? And using logic lens, we have also seen which tokens in the vocab this neuron is firing up. And that all led them to kind of this big procedure here to do global population level analysis. So let me walk you what's going on here. You have all these neurons you care about. Neuron in layer 29, index 2850. You can write it in this way that comes from just rearranging this equation. Then you can get the activating pattern, like see here, we just see if I have operands in this range and operands in this range, this shows the value of this neuron's activation. So this is the neuron's pattern. And then we have also which logits is this neuron activating for. And they turn this logits vector into, again, this heat map. So I'm trying to remember what they're showing you in this heat map here. Okay, so again, they have 4 operand ranges, and they show, I'm trying to remember, I'm not sure whether they focus on just a single logits here and then show this logits value. I guess that would make sense, so they know what the correct sensor is, right? But I'm not quite sure what they are doing to produce this heat map. What I can tell you that the point here is that this heat map here kind of shows what are the output logits that this neuron is activating for relative for the different choices of operand 1 and 2, and they then multiply both of these. And the idea is that with this multiplication, they are kind of capturing not only what kind of operands this neuron is activating for, but also what kind of tokens it is promoting. And once they have this product of these 2 heat maps, they can then pass a lot of data and see what are the prompts for which this resulting heat map is very active for, and they can rank the prompts. Okay, so they do that. Then they also are separately from all this entirety of this process. They have a heuristic, a range such as the difference of the operands is in this range or whatever, and they're just checking whether any prompt in their data fits this heuristic, and then they check, well, here they got top K, and here they got some. If this is larger than some threshold, then they can use this information in some way. So we are going to see how they're going to use that in a second. Okay. So try to remember what we were doing so far. So here, for each correctly answered prompt, they identify the heuristic type associated with that prompt. So then ablate neurons with the highest classification scores in those associated heuristics. So basically here in step 2, they're using this threshold over here. So basically with this threshold being high, that intersection being high tells them that that neuron is implementing a certain heuristic, which is kind of visualized with what you see on the right. If you have this prompt, we can use that intersection to check whether any of the heuristics is what this prompt is activating for. We can then compare accuracy drop to a baseline. We can ablate neurons and see what's going on. Okay, so here on the x-axis, we're seeing the number of neurons that are ablated. And here you can see the accuracy when those neurons are ablated. And what you can kind of observe is that usually the accuracy is dropping sharply when we have a certain number of neurons ablated simultaneously. So it's not just one, but multiple of them. And this is their key result to say, well, we have found these neurons, we have classified them into these heuristics, and we observe when we are ablating few of them at the same time, we are losing the model's behavior. So there are two key things to remember here. They know these neurons are mapped to certain heuristics, and they know that a certain number of them together, when ablated, will drop the model's performance here. These two insights together suggest that this model is using a bag of heuristics, meaning just a set of these heuristics, meaning just a set of these neurons simultaneously to do this arithmetic task. And that's basically it, right? But notice how we have kind of gotten just the population level behavior, right? Like we have explained what this model is doing in general when dealing with these arithmetic tasks. And this is in opposition to what we got out of sparse feature circuits. So with sparse feature circuits, remember that we have constructed by first training transcoder. Then from transcoder, we have built an attribution graph for a prompt. And then from the attribution graph, we have pruned it to get to something like this, right? Here, for a prompt specific, for a specific prompt, you know how the information is building up to reach the answer. So here the question is 36 plus 95. It first breaks it down into these three rough components, and then from 30 and 36 says the number is roughly in the range of 40, right, to 40. And this is similar heuristics kind that we have seen in this other paper, right? Like, oh, is the range of this number in certain value. If it says that we have roughly 40, roughly 50, it's going to give us things like 92, 95. Again, this is maybe connected to logic length result, where if we have two operands in a range of roughly 40 to 50, we then promote a result that's token 92 or 95, and so on. But the point here is that you're getting this information, it's in kind of more direct access to that information. And it's at the instant level. You could, from this other work, also get the instance level insight into which, heuristics are important, because you can tell which neurons are important for a given prompt. And you have described the behavior of the neuron, but it still doesn't give you this nice flow, right? Like it just gives you these three neurons live here, they behave like this, and they're important for this prompt. And you can maybe assume that because, okay, this neuron appears in a lower layer than the next one, there is some kind of flow, right? But remember that with this kind of graphs, this edge between one feature to another has a very, very, very specific meaning that we have derived with a lot of math, which is to say, if I am reaching pre-activation of this target feature, if I change the activation of this source feature, how will that activation change? And we have that edge weight. With the previous work, you don't have that. You just assume there is an edge, and you have no weight between them, right? So it's quite different. But interestingly, both works came to the same conclusion, right? Which is that the models are using some kind of bag of heuristics to do this simple arithmetic tasks. So to kind of contrast these two works, we have our activation patching and using it for circuits. To do that, we first use activation patching to find more important layers. Then we use the neural level patching to find neurons. Then we manually inspected these neurons to describe the heuristics implemented by them. We then classify neurons into these heuristics with this top K overlap. And we have checked what's going on when we ablated these neurons. With the sparse feature circuits, we are doing everything from bottom up, right? Like we are training a replacement model, general, right? Like not, you can think about activation, patching results and components you get as a replacement model, right? But it's a per instance replacement model, and that's basically a circuit. Here you're training a replacement model for the entirety of the model in general. And then for a specific prompt, you create a distribution graph, you prune it, you group features into supernodes, you read computational flow, so far manually, with patterns work automatically, and then they also do some kinds of validations with patching and knocking out things. For example, in the Dallas, Texas, Austin example, they swap maybe Texas with California, and then you expect the output to change from Austin to Sacramento. So they're also doing various things to see, okay, now that they have this computational graph, can they steer the behavior? Okay, so this is also just a little bit more of the breakdown. Also notice that the first line of work is using with neurons, which may suffer from polysemanticity and be activating for two things at the same time. As I said, with this arithmetic work, had kind of given insights at the formulation level, and as far as featured circuits are starting from individual prompts, and because so far they didn't produce automatic way of producing these, they couldn't do the population level yet. I think here, in terms of scalability, this was done to thousands of neurons. Right now, sparse featured circuits, again, are labor intensive because they require this manual part, which I will soon change. In terms of the detail, sparse feature circuits are better because they give you this nice computational flow with edges having very particular meaning and weight. And then, in terms of faithfulness to the original models, so there is no notion of the replacement model per se, like cross-layer transcoder. With cross-layer transcoder, we have the problem of that's an open research problem, right? Like these cross-layer transcoders aren't perfect, and we are starting with something that already at the first place has a little bit of loss of information. Okay, so with all of that, I want to shift gears. I will ask you whether you have any questions, but I just want to say that this is basically a bunch of stuff we have learned in the course, and we still have lots to do. But today I want to go over and kind of review what we have learned together. Before we move forward, are there any questions? Okay, so here's the plan. We are going to do this together. Here. So I'm going to navigate the discussion, and Fatima is going to help us record the ideas. So my idea for this is we go from topic to topic, from the beginning of this course to today, hopefully, and talk about what are the pros and cons of each thing we have learned. And the pros and cons are maybe not the best words. I mean, what are, for example, for pros, let's cover also, if someone asks you, hey, I have heard about SAEs, should I use them? Then we can talk about like when we would recommend someone to use an SAE, right? Or in general, what are the good things about and useful things about this method? And for cons, let's talk about limitations and open problems, whatever comes to mind. So let's start with superposition and linear representation hypothesis. So these are two hypotheses that were the core, key piece to almost every single method we have learned in this course. Superposition, does anyone want to say what superposition hypothesis says? Yes.
It's learning to use more position, or learning to use more features than there are available dimensions or neurons.
That's right. So superposition hypothesis says that our neural models are using more features than they have available dimensions, and that causes a single neuron in a representation to fire up for multiple things. What is the downside of polysemanticity? What is the issue?
Interpretability?
So second?
Interpretability?
Interpretability, right? So if I, for example, if I'm passing data to see for which neurons, for which examples this neuron activates, then suddenly I have this confusing behavior and I can't discern what is the neuron actually doing. Okay, so for superposition, I would say it kind of explains polysemanticity, let's say. And for a con of polysemanticity, anything comes to mind. So maybe instead of thinking about the downside of polysemanticity or superposition, because it sounds weird, think about whether this is a hypothesis, right? We are not calling it an axiom. So this suggests that there is still discussion about it, right? And we haven't really talked about that much, so I don't expect now to have great ideas, but maybe like, you remind me what kind of models did we use to make a point that there is polysemanticity?
There's other large language models to process what inputs we're giving it to try to group them.
Yes, so we have this empirical evidence that things are firing up for multiple things. And that kind of suggests that polysemanticity might be a real thing, right? When we started to do more principled analysis, more kind of still experimental, but more kind of focused on polysemanticity, what kind of model did we use? Remember the experiments where we, was at the very beginning of the class, so a long time ago, but we had the varying levels of sparsity and we had those heat maps. Time model, right? The model wasn't really an LLM, right? And we built this theory around a very simple model. So the full theoretical understanding of polysemanticity and superposition in LLMs, although we have empirical evidence, the theoretical understanding is still very much open-ended. Now, I will show you a paper, and I hope it won't make you hate everything, including me. Let's find it. So this paper had been released in the end of January, roughly a month ago, that says that actually they managed to find what a sparse basis in the neuron space, right? So they say that the whole idea about superposition and everything, that they're quite heavily really questioning it, and actually find experiments that suggest different. So I didn't read this paper carefully to talk you about it, but the point I want you to remember is that when you look into very, very recent works in this space by very, very known researchers in this space, so there is a little bit of credibility from that as well. They themselves say, in this work we question the belief that neuron circuits, like the ones we have just seen, right, from this arithmetic work, are not sparse. Specifically, we show that we can find circuits in the neuron bases that are equally sparse and faithful as those obtained from SAE features. Okay, so this is an issue when you start working in this line of work. Things are changing and foundations are changing as well, right? So you need to be kind of acceptable. You need to accept that things Even the very foundations can change and be questioned and so on. And that can be sometimes a little bit hard to wrap your mind around because if someone says, well, maybe you don't need SAE and premise of SAEs, it makes you question, well, should I ever be using SAEs, right? So for me, I would recommend that you think about, okay, even with these shaky foundations, we are managing to use these methods to get into interesting insights. For instance, remember the Anthropic work with hidden objectives I have shown you, where I said they trained a reward model that's buggy, and then policy with the buggy reward model, and then the behavior propagated. The reward model was trained to never suggest going to a doctor, and then the policy had never, if you ask medical question, no matter how serious, it wouldn't suggest going to a doctor. And then they had the red team and a blue team. The red team is the one who's injected this problem, and the blue team is the one that was given interpretability method to try to recover it. And they said, okay, the result wasn't super strong for this interpretability blue team, but it have given some suggestion that this can be really beneficial, right? So I want you to embrace that point. Like, things are developing, and you are working with buggy methods very often, but you can still find interesting insights with them. And things are, are going to develop, they are going to change. 5 years from now, we might never talk about SAEs again, right? And the foundations might change, and you should be thinking about those foundations as you continue. Yeah?
Why do we care whether in actual LLMs, whether the neurons are sparse, if SAEs serve as a tool to create sparsity so you can
That's a great point. Like, you can think about, oh, maybe neurons, I can get what the SAE gives me from the neurons, but if it's that much work and I can just train an SAE, I'll train an SAE and get it faster, right?
It's a tool.
It's a tool, yeah. So it just depends whether, not everyone will characterize SAE as a tool, right? They will say you need to do this because the information is scrambled in neurons. And they say, well, you can bypass SAEs, yeah. Or at least that's my impression from reading the intro. I would need to read this more carefully. Okay, so going back where we are, explains policy semanticity, but empirical evidence on tone models, and I would add here Fatene, let's say, evolving theory. Okay, and then for linear representation hypothesis, who remembers what that one says?
So if you train something long enough that everything eventually has the same, I guess, features.
That might be that Platonic hypothesis, right? That all the representations across models. Okay, who knows? Raise a hand and I'll pick one person. Kaden? Okay. I'll try to pick people who speak less. Okay, go ahead.
I think, isn't this one where there's almost logic to the vectors, where if you do like woman minus queen or something,
Yeah.
will be king or something like that.
Okay, so let's take an example of the analogy problems. In analogy problems, our features, what do we say they are? So the difference between all of this might be direction, that's kind of a gender direction. So I just said that, I can't help myself. I wanted to ask you, and the answer should be direction, so that makes no sense. What I wanted to say in this example, this is one of these experiments where we notice that features are directions in the activation space, right? So that's one part of the linear representation hypothesis. First, these features are directions in the activation space. And if I want to get a representation of some concept, what do we assume with linear representation hypothesis? Gianna?
It can be the linear combination of other.
Yeah, so we can say features are directions, and new activations, new concepts can be represented as a linear combination of those. Okay, so with linear representation hypothesis, basically the benefit is to enable us a bunch of methods, right? Like sparse autoencoders were the obvious next step coming from linear representation hypothesis, right? So I would say linear representation is enabling a bunch of new methods. What is potential downside, or where the assumption, the hypothesis might break? Raise a hand if you can guess, and let's just try to guess it.
Maybe it's not always like a linear combination to get the representation.
Yeah, right. So it has been shown, there is actually empirical evidence that linear representation hypothesis simply doesn't hold, right? There are things that cannot be linearly represented with other feature directions. There are things that lives, and the best way to think about this, and you will see these phrases, is instead of things living on a line, right, they live on a manifold, right? Things are curving. Which means, for example, when we come after the spring break, we are going to learn about steering, which is, if I have now learned some important direction, such as direction for refusing things, I can, and my direction for refusing lives in a vector space where my representation lives. So what if I just steer my representation, move it towards my refusal, right direction, and now my whole model will start with the refusing. This, the way this is made, actually implemented, is by assuming linearity, and you are just moving along these, linear directions. But if things live on the manifold and you assume, oh, I'm just going to go over the line, you go off the manifold, right? And you're not in the domain where your vectors are anymore, and that becomes problematic. So, there is an evidence that it doesn't hold. So, my kind of practical advice here would be, you need to kind of consider whether whatever you're working in can or cannot be linearly represented and so on. Or if you get negative results, you can't steer, although I expect that you can steer, it can be because things were on a manifold rather than the line, and so on. So, yeah, with all of these, you need to kind of take them as a hypothesis, not axioms. So don't assume they're true and then be surprised when things fall apart after practice. Okay, let's move on to the next method, which is probably SAEs. Right. Okay. So with SAEs, we try to. Do you remember how I motivated SAEs? Or let's put it like this. You meet with other students and they're like, oh, you're in an interpretability class, heard about SAEs, like, what are they, like, when would I use them? What would you say to them? Janta?
You want to extract human interpretable features.
Mm-hmm. Yeah, and can you add just one more adjective to those features of what kind?
I see the question.
With SAEs, we are extracting features, right? Unlike neurons, right, that can be blah, yeah, these are going to be monosemantic, right? So human interpretable monosemantic features. And we decompose our representations into them. I would say with SAEs, one nice thing is that they're really well studied, right? Like we have, when we talked about, let's say, model diffing or sparse feature circuits, there wasn't that much development because maybe they are also younger. But with SAEs, we have already observed, that features can happen, and feature splitting, feature absorption, and this and that, and let's use jump ReLU instead of ReLU, let's use top K instead of L1 sparsity. We need to fix that feature, use the auxiliary loss. We already have a lot at our disposal. Under the cons, all of these issues that I just mentioned, do you remember at the core where they stem from? No, think about how we train SAEs. And then we have as a byproduct then features, feature splitting, feature absorption.
how you induce sparsity in the loss?
Yeah, so with our loss is a trade-off between sparsity and what? What is the other loss?
Reconstruction.
Reconstruction, right. And these two things are fundamentally at the odds with each other, right? Like reconstruction will be the best reconstruction if it can use everything. Sparsity will have best sparsity if it doesn't use anything, right? So we have these two really extreme polar opposites, and when they fight against each other, optimization, we don't fully control it. We are at the mercy of the gradient descent, so we end up somewhere. And all these weird pathologies are the byproduct of this clash between these two optimizations. So cons is, I would say, maybe not, like maybe don't delete it. The trade-off between reconstruction and sparsity causes a bunch of weird problems, right? And then we need to fix all these problems. Another thing I would say is a con is that do we really care about sparsity and reconstruction? Is that our ultimate goal? Not really, right? Like we want to decompose representations into future directions, and we want to do something useful with that, such as finding hidden objectives, right? Or understanding data, or better compressing models, whatever is the goal, right? So I would say the con is we also, by optimizing for the objective, that isn't the key thing, we are also stuck with maybe things that downstream aren't useful. So yeah, sorry Fatima, maybe that's a mismatch between optimization of SAE and the downstream usages. And then evaluation as well, we don't have, I mean in general in mechanistic interpretability we don't have great evaluations. Everything is so new, and if you discover anything interesting, it becomes good enough. But and I will talk about this, how interpretability we had 10 years ago, and then we worked a lot. At some point people have become really disappointed because we didn't really see it being necessary for the best applications that are out there, right? Like ChatGPT didn't emerge out of interpretability. So people have become disappointed, and then again with LLMs, interpretability had gained a new, momentum. But it's really important that we don't end up with a bunch of methods, but no evidence that they are super useful downstream, right? And just reconstructing well isn't the downstream usage, right? We need something more concrete. Okay, let's move on to actually no, wait just a second. So with sparse Hamilton coders, I get my encoder and decoder rate matrices, and I can reconstruct a vector. What is that next piece I need for interpretability?
Yeah, you can like use the LLM when you're talking through it and get like a summary or something.
And we call that, do you remember how we call that?
I don't remember the name.
Like how would you call it? What are you doing by doing that?
Sorry?
What are you doing by doing that, the workflow you just described?
Like feature naming?
Yeah, right.
Generating feature descriptions?
Yeah, generating feature description, right. And so that was the next thing we talked about. And with generating feature description, so that's going to be next slide, but we obviously are getting interpretability, right? What are the potential problems we might encounter with it?
I was just thinking about this because you have such a big dependence on what data you use.
Yeah.
And so you can never guarantee that you have the right name thing.
Mm-hmm.
There's no ground truth really,
Mm-hmm.
unless you run every possible token through it. We don't even know what that means.
Yeah, that's also right. I guess if you had, just as a reminder, we have original model has been trained with certain data, right? And very often we don't have access to pre-training data of models for very few, so like by TIA and Olmo, we have access to all the data, right? So our SAEs and transcoders and everything are trying to replace the original model, right? So for me, it would make sense if I want to have a replacement model of the original model, I use the exact same pre-trained data. But then there is also a question, do I need to place this data in the exact same order? Otherwise, there are some potential weird behavior that can come out of it. And after all, I'm training my SAE with different objectives, so just from that, the data also might be differently captured. So you're right, if there is a huge mismatch between pre-trained data of the original model and what we are using for SAEs, and SAE training data does not capture a bunch of features that the pre-training data has, can our SAE ever learn those features? Probably not, right? There is no data to learn from. So that's one potential issue. Let's say we have similar, these days for getting these descriptions, we use a bunch of tokens. So think about 7 trillion tokens for training SAEs. I don't know how much for generating descriptions, but if you didn't have enough for generating descriptions, you will catch that with our downstream metrics, right? Remember that we are still checking those simulatability scores and all of that. So we have extra checks for those. What else can be a confounder here? What is generating descriptions? Another LLM, and why could that be a problem?
Kind of just depends on its reliability. Maybe if the maximum activating examples are kind of vague, things that an LLM struggles to pick up on, it might not generate reliable working descriptions.
Yeah. So they might not have enough capacity to understand the pattern, which also hints to if I'm using a weaker or stronger model, can have a big effect on the quality of descriptions. Also going back to the data, I wonder, if I have a medical or legal or whatnot for a domain, how different the results would be. Fatima, you had also a bunch of experience with these. I don't know whether anything else comes to your mind.
I mean, I guess it probably depends on, okay, so sometimes the feature is describing something within the input, so this is specific token is activating this feature, and sometimes it's about what this feature is actually going for, so what is this feature helping the model to predict, and there is no real distinction when you're assigning labels to features, that is it supporting a specific next token, or is it just activating based on a specific feature?
Yeah. That's in the Texas Dallas example, there is one feature that says capital cities, but it's not input, it's not what's active, this feature description wasn't derived from the input tokens, rather next tokens are all capital cities, like, I don't know, whatever, Paris, and others. So knowing where the source is can be really hugely influential how we interpret circuits.
Are these like the main motivations for the LLMs that are sparse in the neuron basis? I don't remember the example. Is this like the main idea that if the LLMs are imperfect, and so like maybe, and the data isn't perfect, so it's not that we need SAEs, it's just that like the way that we're describing the original neurons is bad?
I don't know. I didn't read the paper, so I couldn't tell you what exactly that paper is about, but and how they, came to the conclusion they had. But let's, ignore that paper and then think about in your proposal, which is we just need a better method to find these features in the further representations. And then the question is, that sometimes it can fire up the neuron for completely different features. Right? In the 2021 paper with Bird, the illusions of interpretability, the features that their neuron fired up for are so orthogonal to each other, right? Like they're so different. It's really hard to make sense of how we would build interpretability those. So just describing and directly maximum, activating examples and patterns, those probably isn't it. But now what would be that other method that makes sense of everything going on? I don't know. Okay, let's move to next one, which is probing. So today we mentioned probing. Remind me, what is, when would you use it with probing? What is a good moment to think of probing?
When you know what feature you're searching for.
Exactly. So, you give me an example of a feature you might be searching for.
Like truth or
Mhm.
lies.
Truth or falsehood that we have seen a method for. You have an assumption that the model knows what is truth, and you just want to check whether the concept of truth is encoded in the representation. So, pro is a targeted test for a specific concept. Now, if you care about just a single concept, then can you tell me why using SAVs is maybe a worse option than probing? Yeah.
You'd have to create feature descriptions for all of them and then see if a single one matches.
Yeah, so you need to create the entire dictionary of 100,000 features to find whether there is one feature, right? So maybe if you already have an SAE and it comes down to searching this feature description and you can use, correct, then maybe it's okay, right? But if you don't, then having the targeted test is better. Now let's talk about cons. What can happen? What can go wrong? Tell me one bad example of a probe design and why it's bad. Yeah, Betty.
You need to have a simple model when
Mhm.
you're doing your probing.
Okay.
If you do anything more complex, you aren't going to get any. We're actually going to identify the concept that you're trying to find.
Okay, so your conclusion wasn't right. Let's say I have chosen a complex model. I chose 3-layer MLP, and it's really wide layer, really wide matrix. And it has lots of capacity. Do I expect the probing task will be actually successful with this kind of a big model?
I mean, it might be successful, but it's not really.
Okay, I understand. I'm now a bit vague. Instead of successful, let me be more concrete. Will that model have high accuracy?
It'll have high accuracy, but it's more because it's learning the task rather than actually retrieving the info.
Exactly, yeah. So the nice way to train this column is the probe itself can learn, right? And if you choose a complicated probe, and as Matthew had just said, it can have high accuracy, but then you can't tell whether that high accuracy is because the information was already encoded in the original representation, or the model learned it from the representation where that information wasn't encoded. So typically we would use linear probing, but it comes to the same very issue with linear representation hypothesis. If things are encoded non-linearly, you need a little bit of non-linearity to get it out. So some things simply, you kind of choose linear probe to avoid this issue, but then you might never catch concepts. So you might have false negatives, basically saying, with my linear probe, I didn't find this concept, and therefore this concept isn't encoded, but it actually is just a different kind of model. Let's say you read a paper, it says, to use linear probing, we find high accuracy, and the truth is encoded. Therefore, the model is using truth to do the task. What is wrong with that?
Depending on their data set, it could mean nothing. Like,
This is getting really You know, like, again, they say information is in the representation, and we conclude that the model is solving this task because of this information. What is flawed there?
Maybe like equating correlation with causation, there could be other features there.
Yes, but I would like it to be a little bit more direct explanation. Let's say someone doesn't know what correlation or causation is. It is exactly what you just said. Can you just say it a little bit in more lay terms?
I would just say there could be other features or things that the model is doing to solve a task that are also there. We didn't probe for them, so.
Okay, but yes, that's true. But let's say I'm trying to get to yet another possible situation, which is this feature necessarily important for the behavior? Just by it being in the representation, it doesn't mean that the model is necessarily using it, right, for the task. It's as if I gave you a huge book during your exam, and you have the entire book, but it's huge, and I give you only 10 minutes. You had it, but you didn't necessarily use it, right, for it to answer a question. So, and this is basically what you just said, Lucas. Correlation is there, but it doesn't mean it had caused the behavior. Okay, I see we are out of time, so we don't have enough time to go over the rest of it. But I would welcome you, if you feel like it, maybe on the Monday before we meet next time in 10 days, consider going and think